Hi there. Following the previous discussion, let's talk about explainable AI for credit scoring in this lesson. But first, what do we mean by interpretability or explainability? It is difficult to mathematically define interpretability or explainability. According to the cited literature here, there is a subtle difference between the two. On the one hand, interpretability is the extent to which cause and effect can be observed within the system. It is about being able to discern the mechanics without necessarily knowing why. On the other hand, explainability is the extent to which the internal mechanics of an AI system can be explained in human terms. Explainability is being able to quite literally explain what is happening inside the black box. However, in the context of machine learning and AI, explainability and interpretability can often be used interchangeably in the literature. Next question, what do we need to explain exactly? We need to at least explain the contribution of each variable or feature to an individual prediction and also the average behavior of the model and other workings like the interaction between the features. How to make machine learning methods interpretable or explainable? There are two options. One option is to use interpretable methods such as regression and short decision trees. This interpretability is also referred to as intrinsic interpretability. However, the prediction power might not be satisfactory. The other option is to use model agnostic interpretation tools that can be applied to any supervised machine learning model. These methods are also referred to as post hoc methods. This option gives rise to the concept of explainable AI or XAI. How do model agnostic methods work? In a nutshell, we measure the change in the model output by changing the input of the machine learning model. Among all the XAI models in the literature, two are popular for the purpose of credit scoring. The LAM method, which is short for Locally Interpretable Model Agnostic Explanations method, and SHARP method, which stands for Sharply Additive Explanations. This plot here is taken from the original paper of Lam. It illustrates that Lam tries to fit a local model using sample data points that are similar to the observation being explained. The local model can be from the class of interpretable models such as linear models, decision trees, etc. Hence, Lam provides explanations for the prediction relative to each observation. It has a few advantages. First, there are Python Lam library and RLam package, and the model is very easy to use. Secondly, even if you replace the underlying machine learning method, you can still use the same local interpretable model for explanation. It has a few disadvantages though. It does not guarantee that the prediction is fairly distributed among the features. And the correct definition of neighborhood is a big unsolved problem when using Lam with tabular data. Moreover, instability of explanations has also been reported in literature. The SHARP method, on the other hand, in essence calculates the Shapley values. What is Shapley value? It measures the average marginal contribution of a feature value across all possible correlations. An intuitive way to understand the Shapley value is as follows. Imagine the feature values enter a room in random order, and all feature values in the room participate in a game. The Shapley value of a feature value is the average change in the prediction that the correlation already in the room receives when the feature value joins them. It satisfies the properties these four properties shown here, which together define a fair payout. Now we see that one notable advantage of SHAP is that it has a solid theoretical foundation in game theory, and the prediction is fairly distributed among the feature values. The tree SHAP method in particular is a fast implementation for tree-based models, which is key to the popularity of SHAP because the biggest barrier of adoption of Shapley values is the slow computation. This fast computation also makes it possible to compute the many Shapley values needed for the global model interpretations. Further, the global interpretations are also consistent with local explanations, since the Shapley values are the atomic unit of the global interpretations. And a remarkable feature of SHAP is the visualization tools, including the summary plot and the dependence plot. This plot here is an example of the summary plot. Each point on the plot is a Shapley value of a feature and an instance. The position on the y-axis is determined by the feature and on the x-axis by the Shapley value. The color represents the value of the feature from low to high. Overlapping points are jittered in y-axis direction, so we get a sense of the distribution of the Shapley values per feature. The features are ordered according to their importance. However, tree SHAP can produce unintuitive feature attributions, and the computational speed is slow for the other method available called kernel SHAP. Last but not least, both kernel SHAP and tree SHAP are based on certain assumptions. As a result, the returned Shapley values are just approximations, which in some cases can break the four properties for an attribution method. To summarize, one can either use interpretable machine learning methods or use model agnostic interpretation tools to gain interpretability in AI models. Two popular XAI methods in the literature for credit scoring are LAM and SHAP methods. Both are model agnostic, and both have readily available Python packages. SHAP is seen to have the comparative advantage over LAM because SHAP in essence provides fast calculations for Shapley values, and thus has a solid theoretical foundation in game theory, and provides fair distributions of feature contributions. It can be used for both individual and global explanations, and the global interpretations are consistent with the local explanations. But we should be aware that the calculation of Shapley values are approximations.